Today I'm going to discuss some recent joint work with my collaborators, Wenguang, who is here, and also Weinan Wang at USC. So the problem we are considering is about large-scale multiple testing. And I think for large-scale multiple testing, there's no need for motivation. It's a widely studied and applied problem. So I'm going to use genetic example. Suppose we have many genes, and we have, say, two conditions, either under the condition of no disease or under the condition with one disease, another condition, and another disease. We have patients or samples. And each column represents the gene expression of one patient, and we have multiple columns for condition 1. We have another group of people for condition 2. And for a range of applications, we want to make comparison. For each gene, we want to compare, for example, whether the expression levels are different or not. And we have total of m genes. M in this type of setting is very large. So the problem is, I think by now it's quite standard and widely understood. Here's a general principle. The conventional methods, we summarize the original two samples into one column or one single vector of test statistics, be it p-values or z-values or some other summary statistics. And also by now, it's also very well understood the issue of multiplicity. So we need to take that into account. We are going to choose a cutoff along the rankings to adjust for multiplicity. And among all the methods in the literature, I think the best known one is the BH procedure. And it's very easy to explain and very easy to implement. So in BH procedure, we have m hypotheses, and each comes with a p-value, because each row we can summarize by a single p-value. So after getting those m p-values, we rank them from smallest to largest. And the smaller the p-value, the stronger the evidence against the null. So we are going to reject all those with small p-values. But how small is small enough? We define the threshold for any given alpha level, which is a specified FDR level. We define this k to be the maximum of the ith smallest p-value such that it falls below this line. And then we reject everything below that. So graphically, it's easier to see. We line up the p-values from smallest to largest. And for a given alpha, it defines a straight line with a slope equal to alpha over m. So we basically reject every p-value that falls below a given line. And it has been widely used. And last time I checked the Google Scholar, and the original paper has been cited over 50,000 times. It's one of the most cited papers in statistics. And that's p-value. But in addition to p-value, there are also other alternatives. One downside of the BH procedure or the whole analysis is that it's single-mindedly focused on control of FDR. Just want to control the type 1 error. It never look at the type 2 error. If you think about the classical testing problem like Neyman-Pearson, right? Given type 1 error is under control, we want to minimize the type 2 error. And same thing can be done in multiple testing. And the way we did it in another paper is that we summarize the original data into z-values. And each hypothesis, whether it's true or not, is represented by this indicator, theta 1 through theta m. And we assume that all those indicators are IID Bernoulli with some unknown proportion p. And the z's are either drawn from the null distribution or the z's are drawn from the alternative distribution, depends on the value of theta I. And so under this two-group mixture model, the density, the marginal density can be represented as a weighted average of the null density and the alternative. And typically, those quantities, the parameter P, F0 is often known. It's a known distribution. P, F1, they're unknown, and typically they can be estimated from the data. And the optimal multiple testing, we are looking for control of FDR. At the same time, we want to minimize the FNR. You can think of that as an analog of type 2 error. And this can be done by ranking and thresholding of what's called local FDR. We calculate, in the ideal setting, local FDR, if all the parameters are known, local FDR is defined in such a way. And the data-driven method, we need to estimate those quantities. We can calculate by those. And again, local FDR has a similar role of p-value, but it's more precise. It takes into account of the alternative. It tells us, given the data, what's the conditional probability of the data being from the null, from the alternative. So the way we do it is we rank the p-value, local FDR from smallest to the largest. And then we define this k. Then we have the moving average, because I rank from smallest to largest. So this moving average, as you move along, it also increases. And the last time it falls below this alpha, you stop. And then you reject all the hypotheses accordingly. And this can be shown that clearly the method is data-driven, but it can also be shown to be asymptotically optimal in the sense that it controls FDR and minimizes the FNR. And I'm not going to discuss this much further, but if we think about the BH procedure and also this procedure, they have a very important common feature. All these methods, including these two, the method and also the analysis, they begin with one column of summary statistics. In the case of BH procedure, we assume we have one column of p-values, and we forgot what happens before that. And also for this local FDR-based procedure, we assume we have available a column of z-values, and also forget about what happened before. And today we are going to talk about multiple testing of two sparse normal mean vector, two sparse mean vectors. So again, let's look at the notation. We have X sample, we have Y sample. So you can think of the sample from condition 1, sample from condition 2. And each has its own mean, mu X and mu Y. And we want to do multiple comparison of those two long vectors of means. And for many applications, both mu X and mu Y are sparse. And the key message, if we only allow to remember one thing, that's the thing we should remember. That the conventional method of data reduction, which reduces the data matrix to a single vector of p-values or z-values, will suffer from substantial information loss. In other words, once you summarize the data into one column of test statistic, whether it's p-value or z-value, it doesn't matter what you do afterwards. You have already lost too much information. So we are going to start from the beginning. And the intuition is as follows. If both mu X and mu Y are sparse, then most of the coordinates are 0. And if they are 0, they are equal. And we have also the union support, where either one of them is non-zero, is also sparse. And so we have this logical relationship. If both of them are 0, they must be equal. But if you reduce the original data into one column, you did not take that into account. And that causes significant loss of information. So our key idea is to extract the sparsity information on the union support from the original data using some other statistics, and then utilize the logical relationship to increase the power. So we are going to use theta I1 to to indicate whether mu ix is equal to mu iy or not, to indicate that. And mu theta I2 is the union support. So it means that either mu ix is non-zero or mu iy is non-zero. Remember that theta I1 is the main focus. We want to know whether they're equal or not. We don't really care about theta I2 in the original problem. But the main claim is that theta I2 is very useful for us to make inference about theta I1. By reducing into one column, we forget about that part of the information, and that's very important. So the key step is to construct not a single column of test statistics, but a pair of test statistics, Ti1 and Ti2. And then we extract information from the data matrix more efficiently this way than summarizing by a single column. Then try to exploit the original logical relationship. So here's our proposal. Think about the normal case first. If we have two normal samples, here's what we typically do. We summarize by carrying out a z-test for each pair. For each row, we do a z-test. But here, what's different is that in addition to the difference, we also take the weighted sum. And this weight is chosen in such a way that under the normality assumption, they are independent. And here, the normality assumption, as I will make a comment later, is not very important because everything is a function of the average, the sample average. So even if the original sample is not normal, the sample average by central limit theorem, they are very close to normal. Another thing is that here, this T1 is the primary statistic. That's what we used before. And T2 is auxiliary statistic that helps us to make inference about the original hypothesis. So we are going to introduce a bivariate random mixture model. So we have theta I1 and theta I2. Each one of them is a binary variable. So theta itself takes 4 possible values, 0, 0, 0, 1, 1, 0, and 1, 1. And we are going to assume the IID Bernoulli variables. So the pi jk gives us the proportion of each of the combinations. And given the value of theta I1 and theta I2, Ti1, Ti2 has a joint density. And of course, we want to know something about theta I1. But theta I1 and theta I2, they are not observable. Or we can construct a T1 and T2. So we observe the test statistics, and we want to make an inference about those indicate variables. And according to this model, once we have these Bernoulli variables, the joint distribution of Ti1 and Ti2 is a 4-component random mixture. And our goal is try to infer theta I1 based on the pair. So that's our goal. And this mixture model turns out to be difficult to analyze because typically we have 2-component mixture. Now we have 4-component mixture, but this can be done. First of all, the logical relationship tells us that pi 1, 0 is 0 because if theta 2 is 0, theta 1 must be 0. Because if both of them are 0, then the 2 must be equal. So in other words, the 4-component mixture actually is only 3-component mixture. And not only that, under the null, when both of them are 0, we have the independence. And if we have the independence, then the joint density can be factored out. So it can be, after some analysis, the original 4-component mixture can be written as a 3-component mixture. And this will be a useful framework for us to make inference. And for each of those Ti1, Ti2, they have their own marginal distribution. And their own marginal distribution has 2 components. Either theta I1 is 0 or theta I1 is 1. So each has a distribution, and same for theta I2, for Ti2. And we also can write down the marginal distribution density of Ti1 and Ti2 as before. So if we summarize what we have done so far is that we make a point. If we have two conditions, two samples, one from condition 1, another sample from condition 2, what we should do operationally, we should summarize the data into two columns. And theta are the indicators of the corresponding hypothesis. The statistics are Ti1 and Ti2. And before, we don't have the second column. We only have the first column. And because we are dealing with multiple testing, so I want to introduce the criteria. One is we are going to try to control the marginal FDR. And marginal FDR asymptotically is equivalent to the more conventional FDR. Because here we take the expectation, then take the ratio. Instead of taking ratio, then take expectation. And the power of a procedure is going to be measured by the expect true positive. So if you have the same level of FDR, you want to reject as many as you can. And we are going to take two steps. The first step is the so-called oracle procedure. Suppose we know all the parameters in that three-component mixture. If we know all the parameters, what can we do? And then, after we understand the oracle procedure, we want to know what kind of quantity we need to estimate in order to make this procedure a data-driven procedure. So the oracle procedure turns out to be given by this. We need to introduce this test statistic. It's the oracle statistic. It depends on all those quantities. Here I want to point you to this Q star. Q star is the conditional density or conditional probability of theta 1 being 0, the density of T2. It turns out that that's the right quantity to look at if we have all the, if we know everything. So first of all, this is a monotonic function. As you increase the value of lambda, it's non-decreasing in lambda. Because you increase lambda, it means that you are going to reject more and more hypotheses. Because the test statistics are ordered. As you reject more, you are going to have more likelihood to make mistakes. Also, if we define this oracle threshold, the corresponding testing procedure with this oracle threshold is optimal, in the sense that among all procedures that controls the marginal FDR, this procedure has the largest number of true positives. It's the best. But of course, it's not practical. It depends on so many unknown quantities. So in practice, this oracle test statistic is unknown and need to be estimated. If you look at the expression here, it has three terms, three factors, Q star, F10, and F. F10 is a null density of Ti1. And for multiple testing problems, the null is known. For example, if you use Z value, it's standard normal. If you use P value, it's uniform. So this is known. And T1 and T2, that's a joint density of T1 and T2. And we have IID samples of the pairs. So we can easily estimate by a kernel estimate. But Q star T2 is hard to estimate. That's the conditional density of theta 1 being 0, the distribution of T2. We can redefine Q star in a slightly different way, and Q star T2 can be rewritten as a limit of this quantity here. But by itself is not very helpful. But what we can do is we can approximate Q star T2. And Q star T2 can be approximated by something we denote by Q tau, which is an empirical version of this. The reason this is hard to estimate is that we need to know the truth. And of course, we don't know the truth. If we know the truth, we have no problem to begin with. And what we can do is we can look at the p-value based on ti1. And we take a threshold, for example, p-value larger than 0.5. Something large that you're never going to reject. So you make sure that that's the norm. And then we count. You can think of this sort of like a histogram. And this can be, the small q tau is a limit of this. So you can think of this as the CDF version and this as the density version. And a good approximation of the original oracle approach is by replacing q star by this q tau. But of course, this q tau itself still depends on unknowns. So we still need to estimate this q tau. But this q tau has one very important property. It's a conservative approximation to q star. Q tau is greater than or equal to q star. So if we replace q star by this q tau, do exactly the same thing, it's guaranteed the procedure will control FDR and marginal FDR. So we will never lose control by using this q tau. It's more conservative than what's optimal, but we control FDR. In terms of estimation, as I mentioned before, the joint density can be estimated by this kernel estimate. And also this q tau can be estimated by a corresponding kernel estimate. And once we have those two estimates, we can plug in into the original Oracle procedure. And we have the Oracle data-driven statistic. And of course, this quantity is the posterior probability of theta I1 being 1. So it's a probability, it's never about 1. So we take the minimum with 1. And numerical results, which Wenguang will discuss much further later, shows that the choice of tau is not important. It's not sensitive to the choice of tau. But if you really want to do something more sophisticated, for example, we had another paper talk about screening and other things. And if you look at the quantity here, both T2 and T1 play important role in this procedure. So the auxiliary covariate T2 is used to assist inference, and that's very important, and we call this CAS. And here, I only tell you the construction of test statistics. We still haven't talked about the multiple testing procedure yet. It turns out once you have the tested statistics, you can do exactly the same thing as before. So you order them from smallest to largest. You take the moving average. The last time the moving average below alpha, you stop. And then you reject everything before it. And under mild conditions, it can be shown that asymptotically, both the marginal FDR and the original version of FDR of this data-driven CAS procedure are controlled. And before I finish my part, I want to emphasize two things. One is in this discussion earlier, I made the assumption that data are Gaussian. Data are Gaussian, but it's not necessary. Another is we assume the variances are equal. Again, it's not necessary. Because everything is driven by the sample means, the corresponding sample means, and by central limit theorem, whether as long as central limit theorem applies, there's no problem with normality or with unknown variance. So now with that, now I want to turn over to my co-author, Wenguang, and he will give a discussion.
So I'll first talk about some important differences of the CAS procedure with existing FDR methods. And then I will highlight a few important issues that deserve some further explorations. And finally, I'll present some numerical results to investigate the performance of the proposed methods. So first, I want to point out that the CAS procedure is closely related to the problem of multiple testing with groups, which has been extensively studied in the FDR literature. And this is the multi-group model that has been considered widely. And it's first discussed by Afron in his 2008 paper, it shows that, okay, all the testing units can be divided into k different groups. So we use the groups to capture the heterogeneity among the testing units. And in Afron's paper, he looked at the brain imaging data and found that, okay, the front half and the back halves of the brain contain different proportions of the active voxels. And in other words, the proportions of the non-nuls are heterogeneous across the two groups, the front and back. And we have lots of works have been devoted to this kind of phenomena, and then the essential message is that the grouping structure among the testing units can be effectively exploited to construct more powerful testing procedures. And this actually motivates us to consider an alternative strategy to utilize the auxiliary information, the grouping method. Essentially, you can do a two-step procedure. First, you can discretize the T2I into a categorical variable and S, which takes values from 1 to k. And then we can conduct multiple testing using these groups. And this grouping strategy has several important disadvantages compared to the CARS. And so the first advantage of the CARS procedure is that you can see it does not require external data. And this is some information that is obtained for free. So the auxiliary sequence is constructed based on the same data set that we have. And the efficiency gain is due to the fact that we were able to recover some information that is discarded by conventional practice. By contrast, the conventional methods, they also try to utilize some of the side information, like the grouping strategy. However, that information is obtained based on some domain knowledge. And usually, these methods will assume that these groups that are already known or pre-specified based on some external information. However, the grouping is a very tricky issue. Usually, the grouping methods are very ad hoc, and you don't know how to choose the number of groups and how to divide the cases into the groups. And so the CARS procedure does not involve these ad hoc steps. And the second important difference is that our auxiliary statistic has been carefully constructed so that it fulfills the important independence principle. Essentially, if you do the grouping based on some correlated pairs, and then it will distort the null distribution of the p-values, for example. And the BH procedure requires that the p-value must fulfill the uniform distribution under the null. And then if that assumption is violated, and then it will lead to invalid FDR procedures. However, our method does not require that independence assumption. Actually, our independence assumption is fulfilled by construction, and it guarantees valid FDR control. And finally, you can think about the method as, the grouping method is a discretization of the continuous variable as a categorical variable, and this step will lead to further information loss. Our CARS procedure is fully efficient because it can utilize the auxiliary information optimally. All right. So the second point I want to make is that, as Tony pointed out in his previous discussion, that the conventional data reduction process is insufficient, is inefficient because it leads to some substantial loss of information. And this is a more general situation. So you can imagine that we have collected repeated measurements on multiple variables across multiple conditions, and then you have this three-dimensional array. Then the first step of data summarization is to take the sample averages. Then we end up with this data matrix D that contains the sample means. And the the second step of the data reduction is to go from D to some vectors. And for example, if you are interested in making inference about some linear contrasts of certain columns, and then you can figure out some primary statistic to summarize the information. Essentially, it's also a linear combination of the columns in D, and so that's the vector Y. The conventional practice only uses this vector Y and ignore all the other information. And we argue that the sufficiency principle should be carefully examined and probably revisited for high-dimensional inference. In particular, we have provided a very nice example that by only looking at Y, you will have suboptimal multiple testing procedures, and we conjecture that similar issues would exist for other high-dimensional inference problems, including shrinkage estimation, larger scale prediction, and high-dimensional classification problems. And then the other important principle that we have argued is the independence assumption. So essentially, if you have two projections of the original data matrix, Y and S, so Y is the primary column, and S is like the side information. And you need to ensure that A and B, these two directions, are sort of perpendicular to each other. At least it is a very important principle for the multiple testing problem. And I think this is something that should also deserve some additional attention when you do the data reduction. And another issue that we have focused on in this work is to combine the primary and auxiliary sequences in larger scale inference. And at a more abstract level, you can view the CARS procedure as sort of a nice application of the pulling within idea that has been considered a long time ago in John Tukey's work on the philosophy and the principles of data analysis. So the pulling within idea can be described as a two-stage data combination procedure. The first stage is to gather quantitative indications from within different parts of the data. So we have the same data set, but there are different parts of the data would contain useful information. For example, in multiple testing, you are interested in making inference about the sparsity structure. And the sparsity structure is not only contained in the main column Y, but also contained in the auxiliary column S. Okay, so that's the first important message. And secondly, when we apply the pulling within idea, then we needed to come up with an efficient strategy to pull the data indications into a single overall index. And so in the CARS procedure, we have developed a single index. That is the CARS statistic. And actually, we show that this statistic is optimal for combining the two pieces of information for the testing problem. And so finally, I want to discuss the bigger picture about the current status of the multiple testing. So at the beginning, we have the BH procedure, and people have known that, okay, the BH procedure is not fully efficient because it is conservative for FDR control. Let us consider this non-null proportion, pi 1. So the BH procedure only controls the FDR at level 1 minus pi 1 times alpha. Alpha is the nominal level, so it's conservative. And then there have been a lot of works in the literature. All these are very influential. It shows that, well, if you can estimate this non-null proportion and incorporate such information in the original BH procedure, and then, for example, instead of testing the hypothesis at level alpha, you can test it at FDR level of alpha over 1 minus pi. And then you can improve the power. And our work is sort of along that line and pushes further to discuss, to incorporate the more useful structural information in the analysis. So we argue that in light of the auxiliary sequence, the proportion will become heterogeneous. And if you have heterogeneous proportions, then you can actually utilize a more refined information to further improve existing methods that only incorporated the global propulsion. And so this is sort of the connection to existing works. And the other interesting thing that I'm really excited about the work is that people have actually tried to do this conditional propulsion estimation. And there are several papers that have proposed the methods, but all these are not very satisfying. And if you look at our CARS procedure, and we have discussed, so Tony has discussed the estimation of the Q tau, and that idea can also be employed to obtain a non-parametric estimator for the nanopropulsion. And we did not study that in the paper, but we conjecture that estimator here would have some very good numerical properties, and also the theoretical properties of the estimator should be also strong. And so these are the connections to existing works and some important issues that we have resolved. So next, I'm going to present some numerical results. We will consider the simultaneous testing of 10,000 hypotheses, and the nominal FDR level is set to be 0.05. We are going to compare the following methods: the Oracle procedure, the data-driven procedure, and these two have been discussed by Tony, and the BH procedure and the adaptive z-value procedure. Also, Tony mentioned both of the procedures at the beginning of the talk. And finally, we would like to compare our methods with a method called uncorrelated screening. It's sort of connected to the grouping idea that I mentioned at the beginning of my discussion. And we also developed an R package called CARS that can be used to implement the data-driven methods. In the first setting, recall that we have two columns, and both columns are very sparse. And so the total number of tests is 10,000, and so K, 2K is the number of non-zero coordinates. And then we have two vectors, and both are very sparse, and so the non-zero elements are the first 2K, but they only differ in the first K locations. And we would like to vary K from 100 to 1,000 to investigate the impact of sparsity on the performance of different testing procedures. And we apply all the 5 methods we mentioned before, and then we plot the corresponding FDR level and the corresponding power of different methods using these two panels. And then from the left panel, you can see that all the methods are valid for FDR control. And the uncorrelated screening method is a little bit conservative. And on the right panel, you can see that, well, so there are several things going on. Let me just point out. So the BH procedure has the smallest power. It can be improved by the adaptive z-value method. And so both the BH and the AZ method, they are univariate methods. So they only use the primary statistics. And actually, the blue line here is the best thing you can do for a univariate procedure. That's the optimal one for univariate procedure. You can see that if you utilize the additional information from the auxiliary sequence, you can improve the power, like the uncorrelated screening. However, uncorrelated screening, because it's a screening procedure and it's essentially a grouping method, it discretizes the continuous variable, so it leads to loss of information. But if you use CARS, and then it can further improve the power. And we can also get a sense that the power of the efficiency gain of the bivariate methods will be more pronounced when you have a more sparse setting. Okay, so K is like the number of non-zero locations in the original testing setup. In the second setting, we try to investigate the effect about the informativeness of the site information, or the informativeness of the union support. And if you still remember Tony's previous slide, so you have two columns and you have this union support. And if you look at the, so K1 is the number of non-zero coordinates. So K1 is actually the union support. And then K2 is sort of the number of locations with varied effect sizes. And if you increase K2, so here we fixed K1, but if you increase K2, then the overlap between the primary parameter of your interest and the unit support, the overlap will increase, and therefore the auxiliary sequence will become more and more informative as you increase K2. And then we can sort of see a pattern that the gap in the powers will increase as you increase K2, and so that's so our simulation result is consistent with our equation. So you get more when you have a more informative auxiliary sequence. And so the third setup is sort of concerned with the effect, the impact of the effect sizes on the performance of the testing procedures. And we have some similar messages that all the methods are valid for FDR control, as shown in the left panel. And then the power gain would be relatively large when you have some increased mu zeros. So if the effect sizes increases, then we have a larger gap somehow. Okay, so a very quick summary of the numerical results. So all methods control the FDR at the nominal level, and the univariate methods can be greatly improved by bivariate methods. And the CARS method will dominate the uncorrelated screening because we can utilize the auxiliary information as a continuous variable instead of a discrete variable. And then and these are the two settings we found are particularly interesting, and it's consistent with our iterations. When signals are more sparse, when the supports have more overlaps, then we have more efficiency gains. I will turn to Tony to give some concluding remarks and answer possible.
I just want to quickly summarize the main points we made in this paper. I think, to me, the most important message is the first line. Yeah, for testing two sparse objects, reducing the data to a single vector of differences, no matter what you do, whether it's p-value or z-value, you have lost too much information. And for independent tests, what we propose, the CAS procedure, is shown to be near optimal. And also the numerical results Wenguang just presented show that there's quite significant improvement over the traditional method. So I hope that we all remember the first message, and the rest are just technical details. And thank you.
So first, I want to thank the organizer for this discussion meeting. I'm very pleased to be here in London. And I want to congratulate and to congratulate the authors of this course procedure, which is really nice. So congratulations. It was really a pleasure to read this paper and to go through the details and so on. And what I want to do now is to discuss this procedure and to underline the Bayesian flavor of the procedure, in fact. So just to give some intuition between all this kind of procedure of Bayesian way to capture the structure of the null hypothesis. Imagine you have some data P, that is generated with some true P in a model, and you have M null hypothesis for P, okay? So you have M null hypothesis. And theta I codes for the trueness or the falseness of the null hypothesis. So theta is equal to 0 if it is true. And so in real life example, theta is not something just IID over all the direction. It has some structure. Okay. So one example is when theta is something piecewise constant, for instance. Other possibility is sparsity of the Ti, and so on. And the Bayesian trick, as I see, I call it Bayesian trick, is to build adaptive procedures so they will incorporate this structure. but in a very simple way, because you just have to put a prior on theta, a prior distribution, that follow this structure, okay? So for instance, if you are in the setting where theta is piecewise constant, you just put a Markov prior, you generate like a Markov chain, okay? If theta I is equal to 0 often, so if you have sparsity, you just put something like spike and slab, something like this. So this is just the prior distribution that you can specify. You can fit the prior by estimating the hyperparameter, and then you just have to compute the posterior distribution, and it will give you an optimal rule. So that's really the beauty of all this Bayesian way to build multiple testing procedure. And at the end, you expect that this procedure, this kind of procedure beats a BH, like controlling the FDR and having a better power. Okay? So that's the general picture. So now I stick to the framework of the paper, so just Gaussian and with sample 1. So very simple case. I have two sample X and Y with means. I test the null if they are equal or not. Okay? And as the author said, you have the test statistic, which is just the difference. So it's exhaustive statistics. Okay? And you have a covariate, which is a sum, or a scale sum. Okay, so here I have some illustration. So it's like in the paper, like in the simulation, the numerical experiment of the paper. You have mu x in black here. So this is a black signal. Mu y, is in red. And what we can see is that both vectors are sparse. So you have a lot of zero that is shared in common. So here the null hypothesis is true because the two mean are 0, so they are equal. And here the two mean are equal, but they are not 0. But the null hypothesis is also true on these items. And here in this small area, you have signals, so you have different means. Okay, so H1 is false here. No, H0 is false here. Okay, so this is the typical setting where cars can help us. If you compute now the expectation of T1, so if you make the difference and you take the expectation, you have the black means, the black mean here. So it's really the typical case where the test statistic has some non-zero expectation under the alternative, and under the null you have 0. Okay, and you want to use this test statistic as usual. But here you have T2 as well, so the auxiliary covariate, and the expectation of T2 is in red here. And what we can see with this picture is that when T2 is small, you are likely to be in this area. So you are likely, the null hypothesis is likely to be true. And that's precisely the information that carries T2. Okay? And that's what you want to use. And that's what cars use. Okay? So instead of taking the classical LFDR statistics, that is just conditioning with respect to T1, you condition with respect to T2 as well. And what is the effect? You have a correction term here in red. So in the setting, in the classical setting, so you have computed this correction term here. And what we can see is what? So what is this picture? So in the y-axis, you have the correction term. In the x-axis, you have T1. And I display the correction term for several values of T2. Okay? So when T2 is small, what does the correction term? It penalizes the large value of T1. So it means that it will help to accept the null hypothesis. Okay? And when T2 is large, what does this correction term? It will help to reject the null hypothesis because the correction term is close to 0. Okay? So really incorporating T2 helps. So what does cars after? So this is Oracle, and what does cars afterwards? They just estimate this Oracle rule with kernel density estimators. The selection rule is best statistics with cumulative sum smaller than alpha, so as usual. And they show, so what is proved in the paper is the FDR and power consistency results. Okay? under three conditions that I want to discuss. So first, the mixture modeling. So the way the prior is generated should be true. It should be the model, in fact. So the prior is really the model. Second condition, all the parameters are fixed with m. So you for instance, pi 0, the probability to generate a 0, so equal means, is something that is fixed. And then m tends to infinity. And the third condition is that the kernel estimator should be efficient, so they should be consistent so that the data-driven procedure estimate well the oracle procedure. So I want to discuss the second assumption here. So all the parameter is fixed. This excludes, in principle, the case where the data is sparse, because under sparsity, what does this mean sparsity? Is pi 0 tends to 1. So pi 0 should depend on m. I suggest this kind of control that take into account the sparsity. So what about what I call the uniform? What is the uniform control of the FDR? So BH does this kind of thing. And maybe we should look at this. So here, what is delta is the difference of the mean. The norm 0 is the number of non-zero components. And Sm is something small with m. Sm over m tends to 0. So what about this kind of control? So that's what I'm going to discuss now. Can we use this methodology to ensure this kind of FDR, uniform FDR control? So that's my point today. Okay, so for having this, I discussed some possibility, which is to modify a bit the prior. So I take the, so in the paper you have a spike and slab prior. It means that the difference of the mean is generated according to a spike and slab. So spike is the Dirac in 0, so this is the spike, and the slab is gamma, this is the density. And the sum also is like a spike and slab, but with a different proportion with the spike, because you want to generate two zeros, so that the expectation of T2 is 0. Okay? Bon. And the point is, of course, we can try to estimate the slab gamma by making some kernel density estimators. But maybe one thing that we can do to stabilize the procedure is just to use a very simple pre-specified slab like Cauchy density. So it has EV tiles. Okay, so let's take gamma equal to the Cauchy density, why not? And the point is that if you look at the correction term, so as before, you still have some improvement by taking into account T2. Okay, this is qualitatively the same picture as before, but this is computed, the correction is computed with the Cauchy, the spike and slab Cauchy prior. And the point is when T2 is small, the large value of T1 are penalized, and when T2 is large, it helps for rejecting. So you have the same qualitative picture, even if you take a slab very simple like Cauchy. So why not using that? So we can discuss a Cauchy slab version of cars that compute this posterior probability. So this is Q value, but this is the same than the local FDR. So the probability to be 0 given T1 and T2. And the point is that if you use a Cauchy prior, then the point is that this is all these quantities are known because you put just Cauchy, you know what is the Cauchy. But the only term that you should estimate are pi 0 and pi 0, 0. And you can do that by marginal maximum likelihood, for instance, from T1 and T2. So the procedure is very simple, and just after you reject the Q value smaller than alpha, and you're done. Okay, so my question today are, if you do that, can we recover this Cauchy slab cars version? Can it recover the uniform FDR control under sparsity? And can we show that the power is always better than BH? So for the first question, I have some hope that this is true. In fact, we have studied the univariate version, so without covariate, but just the univariate version with Ismael Castillo in a paper, and we get a property like this. So, okay. So I believe that it's true, but I have no proof for now. And for the power, so I have done some very simple simulation, but preliminary simulation in the framework of Carr's paper. So what is this? We have a weak signal, so the mean are not very different. Strong signal, so the mean are very different. This is FDR and this is false negative rate, so type 1 error, type 2 error. Okay. In black you have BH procedure, in blue you have the Oracle version of Carr's, and in red you have the Cauchy-Slab version of Carr's. And what we can see is that the FDR control seems okay, so we have a kind of conservativeness, you see, here, sorry. And for the type 2 error, when you have weak signal, you don't see anything, but that's reasonable. And if you have strong signal, then you do something between BH and the Oracle cores. So it's not too bad. And again, what is striking here is that the true data is not generated as a Cauchy. The true data is just the true data, so the same simulation setting, but the procedure uses the Cauchy prior just for as a tool. Nothing is Cauchy in the data. Okay? And it still has some properties, some interesting properties. Okay, so my message. So I really like the course paper. So especially, of course, the way the covariates can help to make the multiple testing decision. Also, something else that I did not discuss here, but they really solve the way to maximize the power given that the MFDR is controlled. So the Oracle version of Carr's is really solving an important issue. They also propose some extension and package, so it's really nice. So my discussion today was about the uniform control of the FDR. And I suggest one direction. So to stabilize the estimation of the slab, maybe just use a very simple slab. And under sparsity, it could be sufficient, maybe, to have a uniform control of the FDR like BH does, sorry, and to have a good power. So still incorporating the T2 in a good manner. Okay, so that's what I wanted to say today.
All right, well, I'd like to also thank the organizers for inviting me, and also I really enjoyed looking at this work and diving into it. And so I'll just have a few comments. It turns out actually quite similar to Etienne's, actually. We had a similar line of thought. So I think I was just reminded that the person who the second respondent often has a more critical tone, and I'll get there, but I start with a lot of sort of attraction to this work. I think it's really beautiful, and I saw it like this: as if local FDR is just the conditional probability of the null being true, then Carr's is the same thing. It's just adding in this second statistic, and it's just that's wonderful. It's a very elegant place to start, and I think it's really nice. And I think once you put it that way, it's very easy to understand as a generalization of local FDR. And then to that, and I actually came up with the same sort of reformalization as Etienne, is that while for the purposes of estimating the Carr statistic, you need to look at it like this, and you estimate the Q star criterion. I definitely see it easier to think about like this, that it's the local FDR modulated by this term that measures the informativeness of this auxiliary statistic. So this really speaks to me. I think this is really neat. It's basically saying, if there is no information in the auxiliary, if there's no information in the primary relative to the secondary, then this will just be 1. But if this is less likely, if this is more likely, if there's some relationship in that joint bivariate distribution between T1 and T2 that makes T2 more likely given a particular value of T1, that's going to pull down the local FDR and give you this extra boost in power. I think that's very elegant. But of course, this is not really practical to estimate. You'd have to do a kernel density estimate for every possible conditional value, and so of course it's more direct to work with finding a kernel density estimate for the bivariate. So that makes sense to me. So I thought, actually, I was very excited that there was a package produced for this, and so I wanted to get on and apply this to some data, and I'll talk about my area of application in a second. But what I thought is, like, okay, I'm going to visualize and I'm going to plot this factor so I can actually sort of see how the procedure is working. What is this actual sort of multiplier? And what I'll do is I'll just estimate naively as a ratio, as the local FDR estimate actually obtained from their own package, and the produced CARS statistic. So I started by just trying to reproduce some of the results in the paper, which we've seen just recently. That's sample sizes of 50 and 60 at 5,000 tests. In this case of there being just exactly as Etienne illustrated, 1,000 tests where the mean is different from 0 overall, and half of them have some differential effect. So that's exactly the same setting that we saw illustrated before, although I did pick up a different standard deviation as was used in the paper. And so let's see if we can make sense of these. These are the things I looked at. So you start with a histogram of all the test statistics, and hard to see, but there's a slight fattening of the right tail because there is effect. This is a T1 statistic, evidence for there being a differential effect. Up top is the local FDR plotted as a function of the statistic. And what I've done is actually I've drawn the curve 3 times for the 3 different conditions that we have in the data. So in the black line, is the case where both nulls are true. That is, there's no mean effect and there's no differential effect. The red line is for the points where the differential effect is null, there is no difference, but there is an overall mean effect. And the green line is when there is both an effect. And so normally if you're just using the local FDR to make a decision, that would be, you pick the line where you pick the point where the line crosses under 0.05. Just for illustration, I also put on the vanilla Benjamin-Hochberg filter there. Now, if I do this with the CARS statistic, again, I'm making 3 plots for the different types of data where the x-axis is the T1 statistic and the y-axis is the CARS statistic, but just partitioned by these 3 states, and you see exactly what's happening. So we're getting this boost. So for the case where there is a mean effect, these are suppressed down. This is exactly what Etienne was plotting, but this is actually with real simulated data. And then you actually get a penalty effect. Now if we plot this ratio, you see this very clearly. So there's this penalty that makes these values larger when there is no mean effect, but when there is a mean effect, we're getting this suppression here that gives us the extra power. So this is really nice, you can see, whereas before the local FDR was less powerful than Benjamin and Hochberg, now we're actually getting greater power than Benjamin and Hochberg by using this information about the average effect. So I thought that was really just a nice way to sort of understand that and see what's going on, following this exactly the same path as Etienne. So I tried to, my interest is in brain imaging, I'll get to in a second, and so I really need to have 100,000, 150,000 elements, and so I started cranking this up to 10,000, and again, no problem, get the exact same sort of behavior. When I tried to get it up to 100,000, kind of all hell broke loose. I'm not sure what happened. I think there actually were some problems with the kernel density estimation. There is a sparse mode that's advertised, but unfortunately the one on your web page doesn't have the sparse function in it. So I wasn't able to try out the sparse.
There's sparse option, right?
Not on the one on the web.
Okay,
Not on the one on our on the distributed version. So unfortunately, this falls apart. We're getting very crazy values. So I don't think there's. I know that you've paid attention to this one, but unfortunately, it wasn't available. So I wanted to also look at a case with increased sparsity. So now if I do something pretty punishing here, where if I look at the effects of looking at the same number of non-zero effects overall, 1,000, but only 10 effects where there's a differential effect, then it actually just exploded. I got no answers again, and I think this is the sparsity case where I really needed that because basically this is not your work, but actually the NP library just failed it threw an error. So definitely I can't wait to try out the sparse option on that. So let me just say a little bit myself and what my interest in this is. So I'm at the University of Oxford's Big Data Institute, a place where we're trying to combine lots of big data sources, ways of measuring people and data, and analysis and sort of sharing data. I kind of live in this area, developing analysis methods, and also I work on some data sharing. My specific interest is in brain imaging. So I focused mainly on functional magnetic resonance imaging. This is a really exciting technique where you can put people into the scanner, and due to the differential magnetic properties of blood, just as blood goes from blue to red as it gains oxygen, it turns out it goes from a paramagnetic to a diamagnetic state. And so you can actually, without injecting you with anything, you can actually measure the local concentration of oxygenated blood, and that lets you put someone in the camera and say, in the magnet, and do some very simple tasks, for example, tapping their fingers, rest, tapping their fingers and rest. In general, most of the brain doesn't change. And this is key. This is the sparsity, right? But the part of the brain that actually is responsible for moving your hands will show this differential effect going up and down. And just as an illustration, no one ever does these kind of experiments. They're too boring. The psychologists do experiments like this that actually have many different conditions in them, many active recall conditions, and we actually end up using some sort of general linear model. But well, I'll show you why I still think this work is important for this. But just to say, for this main effect, we get lots of sparsity. There are lots of parts of the brain, if the experiment is well designed, that show no response, but there is an overall response at some areas. And so the interesting things, and what excited me about this work, was then actually seeing differential effects. This is just something to note, that this is evidence that we have some strong differential effects. So for fMRI, for a number of different experiments, I just point you to this Cohen's d. So there's a distribution of effect sizes, but there are a number of effects where we get an effect size over 0.8. And so this is good. This is saying there's evidence that the T2 statistic is going to be quite far from zero. There'll be places where it will be exactly zero because there is no brain response, but when there is a response, it should be rather easy to detect. So one big data project that I've worked on is something called the Human Connectome Project. It collected data on 1,200 subjects. This is pretty exciting. It was a population sample. Actually, it's based on a twins registry, so it really should be a representative sample of the population, at least of Missouri. I'll just focus on one part of this data, which is fMRI data for one particular task. The data I had at hand on my laptop that I want to play with is actually not 1,200 subjects, but just 78. There's actually some complications. The full 1,200 includes families and related individuals, and didn't want to mess with that. So these are 78 unrelated subjects, and they're all, in this task, given a working memory task. They're shown a sequence of letters, and they had to identify, seeing only each letter one at a time, when was their repetition going to back. And it may sound simple, but it's a really hard task if you've ever done it. You just have to, on a running basis, remember what happened 2 ago, and it doesn't matter if, for example, this X here came back, don't ignore that. And the control condition is just whenever you see an X, press. And so this is an example of a well-designed fMRI experiment. The stimuli are exactly the same. The number of times that you press the button should be the same. So visual, motor responses should be matched. So those, when subtracted, should give you no effect. And so this is about the sparsity of the main effect. So this in general should be sparse, and we'll only see areas changing that are responsible for maintaining some letters, what they call working memory. So now the question was, now I'd like to try to see how are people different in this working memory response for some covariate. Ideally, I'd like a continuous covariate, but we don't have that for this tool, and I'd like to discuss that. But I'll just say I just used IQ, split it between high and low, and was happy to find that this is the test statistic for the difference between high and low IQ for this working memory experiment, and found that the cars indeed detected differences between these two groups, and Benjamin Hochberg, FDR, could not detect anything there. So that actually, very small evaluation, but worked out well on data. So I'll just skip this. I'll just said those things, and just say that I think there would be great value to extend this to the case where you have a continuous covariate, not just comparing two groups. And I think it actually, a covariate that's centered is orthogonal to the mean. I think it might actually work. And maybe the word covariate always seemed kind of funny to me because, yeah, I mean, it's the mean. You're kind of adjusting for the mean, but we can talk about that more. And with that, I'd like to second the vote of thanks for this work.
First contribution is by Felipe Medina and Milan Stelic. They congratulate the authors for their work on ranking and screening large 2D sample inference, and they point out a potential issue that arises in the context of differential expression studies, where biological samples are genetically heterogeneous. And they basically suggest a modification of the model, and by adding fixed effects accounting for the effects of genetic background of individuals. And basically under their model, they have show that the primary test statistic T1 becomes biased under the null. And they say, of course, this bias is unobserved and shifts the center. And they say this then will reduce the empirical power. And they argue that given the increasing need to study multi-ethnic cohorts and admixed populations methods for performing these differential expression studies, they need to be able to handle sources of variability like the ones found in these expression quantitative trait loci studies. Basically, they think that adaptation of the method, like the CARS method, to consider this kind of issues is an interesting direction for future research. So this is the first contribution. Second contribution is by Trabak Banerjee and Gaurav Mukherjee. They would like to congratulate the authors for developing this highly potent CARS procedure, and they have also studied the efficient use of site information for improving mean squared error in the estimation of several contrasts. They suggest a new method which they called ASUS, Adaptive Sparse Estimator Using Site Information, and they study their performance compared to competing models that do not leverage site information. And they see that their method, ASUS, using the site information, exhibits superior performance compared to these other methods without the site information. So they stress that the general idea behind CARS and their proposed method ASUS is of adding auxiliary information to primary statistics for improved performance, and this is very useful. But they also argue that in situations where there are multiple covariate sequences, it is unclear how to modify these procedures, ASUS or CARS, to construct an efficient strategy to using this auxiliary information. And they point this out as future work.
First of all, I want to thank both Etienne and Thomas for the wonderful and insightful discussion. And they certainly have pointed out a few things that we didn't realize or we didn't pay attention before. And I think both of us, I'm speaking for Wenguang without asking him first. Both of us, neither of us think of ourselves as a Bayesian. We use, we use Bayesian ideas. For example, we use the random mixture model for our work, but we never think of it's just to me personally, it's a tool. But we did use empirical Bayesian method for estimation and also for deriving the method. And Etienne pointed out a pure or more pure Bayesian method, and it never occurred to me, but I think it would be very interesting to look into that much further. For example, you point out using this Cauchy slab. And it would be very interesting to see the effects of fixing a specific prior without, say, empirically estimate the prior, and to see how that's going to work, and also the effect of the prior on the performance of the procedure. It would be a very interesting, I think, separate and very interesting work to look at that, especially the related questions you mentioned at the end about the performance. Another thing is about this uniformity. And also it didn't occur to us to look into that, and we will certainly think about that much more carefully. So, and your comments is more on theory and methodology. And Thomas' comments are very interesting, especially his line of applications, because that picture, we didn't have the data, and also we didn't look at that. Otherwise, we'll put in our paper to show that the advantage of our method over the BH procedure. But more importantly, I think scientifically, it will be very interesting to look at some of these type of applications where this T2 can really enhance the performance of the multiple testing procedure. So if you have, I'll ask for your slides, and if you have more specific, say, data sets or something, maybe we can collaborate in the future. Yeah, those are very, very interesting questions.
I'll just add a few more points in addition to Tony's discussion. I really like the two discussions on the nice interpretation of the CARS statistic, and in particular the impact of the impact of the T2 on the T1 and the informativeness of the T2. And I think in general, I'm very interested in exploring further, like when you try to reduce a high-dimensional matrix to maybe 1 or 2 vectors, then what can be the potential efficiency loss? And that might be, while this kind of ratio might provide some insights on such directions. Secondly, I really appreciate that also both discussants mentioned the numerical stability of the CARS procedure. I will certainly add that sparse option after this meeting. And actually, in the paper, we had already discussed a sparse option. So if you have really, really sparse signals, then we have a more conservative methods that will guarantee the FDR control. However, we are unclear about how the power gain would be compared to the BH procedure. That's something that we will further investigate. And then further points about the numerical studies. I really like intense discussion about the Bayesian perspective, and I think it somehow the frequentist properties of these Bayesian procedures need to be investigated. However, I do realize that it will be more stable compared to the kernel methods that we have proposed. And so that could be one of the advantage of using a pure Bayesian approach. And a more direct approach for the estimation problem, you'll see that now in the CARS procedure, we have estimated the numerator and the denominators simultaneously and then do the ratio. Then a more direct approach is to estimate that posterior probability directly using some kernel methods. And I think there are some new developments in the literature that we are thinking of developing some new numerical strategies to handle that posterior probability directly in a frequentist way. And so that's also a very interesting direction we will pursue. Also, I have made some notes about some written comments. And so the first is that the application of the CARS methods to the shrinkage estimation problem is by Trumbuck and Grubb. And that's a very nice direction. In general, as I discussed in this, in a part of my talk, is that I feel that the sufficiency issue is a fundamental issue in high-dimensional inference, and it's been the foundation of statistics, but recently has been ignored because there are so many new issues in high-dimensional statistics. But this classical idea should be revisited in some sense. And so I'm glad to see that not only for two-sample multiple testing, but even in shrinkage estimation, there are similar phenomena that you can construct some auxiliary sequences to improve the efficiency. And I can imagine that similar ideas could be applied to like high-dimensional prediction, classification, and other questions. So I really appreciate that comment as well. And finally, I think it's very important to further investigate the situation with multiple sequences that mentioned by the other written comments. I feel that the issue is non-trivial because at least for the CARS procedure, it's unclear how you can implement such a density estimator with more than one sequence. I think even for the two sequences, the method is already unstable in some of the scenarios. And so I think there must be some newer ways to deal with the multiple sequences. And then one possible direction is that you can probably find a best direction of some projections of the original matrix so that you still end up with one sequence, but that one sequence might be probably more informative than any of the original sequences, but how to find that optimal direction of projection would be open issue. Or maybe there are some other more smart ways to handle the side information problem. Okay, that's all that I want to talk about.